Welcome DIKWP, 小工 aboard. Your learning journey starts now. Alright, let's dive right in. We're talking about complexity, but not just the old O of N stuff. That's like trying to understand a symphony by counting the number of notes. It misses the melody, the harmony, the whole point. Traditional metrics work great for simple algorithms, but when we're dealing with AI systems that actually think, learn, and decide, they fall flat. They can't capture the real complexity, especially the semantic kind. Think about those big language models. They're powerful, sure, but often seem like black boxes because their internal purpose or intent isn't explicitly modeled. This leads to all sorts of issues: weird outputs, unpredictable behavior, even ethical headaches. So, what gives? How do we get a handle on this mess? So, how do we fix this? Enter DIKWP. Think of it as the DIKW pyramid, which you probably know. Data, information, knowledge, wisdom gets a crucial upgrade. We add P for purpose. Why is this huge? Because it forces us to look at the system's goals, its intentions, its value judgments. It's not just about what the system knows, but why it's doing what it's doing. This layered approach, DIKWP, lets us dissect cognitive systems. The data layer is raw sensory input. Information is structured patterns from that data. Knowledge is rules and concepts. Wisdom is decision-making and strategy, and purpose. That's the top layer, the goal-driven behavior. This isn't just academic navel-gazing. It provides a framework to measure complexity at each stage and see how they interact. It's holistic, it's semantic, and frankly, it's way more useful than just looking at CPU cycles. Okay, let's get specific. How do we actually measure the complexity at each layer? For the data layer, it's pretty straightforward. C sub D equals O of N. Just the sheer volume of raw inputs. More pixels, more sensor readings, higher N, higher complexity, simple. Now, the information layer, C sub I equals O of F of N. This is where we extract meaning, patterns, features. Think edge detection, feature vectors. The cost depends on the algorithm. F of N could be linear, log linear, maybe even polynomial, if things get fancy. Then, knowledge, C sub K equals O of R times K. This is about searching and reasoning within your knowledge base. R is the number of relevant rules or facts you need to check. K is the total size, bad indexing. R could be close to K, good indexing, much better. Wisdom, C sub W equals O of S times G. This is decision-making. S is the state space, G is the number of strategies you evaluate. Chess, anyone? Finally, purpose, C sub P equals O of T times L. How often do you switch goals T, and how many feedback loops does each switch take, L? Think task switching in a multi-agent system. Each layer has its own beast, its own bottlenecks. DIKWP lets us pinpoint exactly where the system is struggling. Now, here's where it gets really interesting. These layers don't operate in a vacuum. They talk to each other. The output of the data layer feeds the information layer, and so on. This coupling changes the overall complexity. You can't just sum up the individual layer complexities. Sometimes, interactions make things worse. Positive coupling, lambda ij greater than 0. Other times, they make things better. Negative coupling, lambda ij less than 0. For example, if your knowledge layer is rich and well organized, it can actually simplify decisions in the wisdom layer, reducing the effective search space. That's a negative coupling, lambda k w less than 0. Or, if data quality drops, the information layer might have to work harder, increasing CI, even if CD stays the same. Systems evolve through this. Initially, complexity might just add up. Then, as layers interact more, things can get messy, faster than linear growth. But eventually, good systems learn to coordinate, achieving stable synergy, where interactions become efficient, maybe even lowering the overall complexity. Understanding these dynamics is key to building robust AI. Let's ground this in reality. Take AI education systems. Their main goal, the purpose layer, is usually pretty stable, help students learn. So, CP is low. The trick is optimizing the information and knowledge layers efficiently using things like knowledge tracking models, autonomous vehicles, massive data deluge from sensors, so CD is sky high. Information layer is also a major bottleneck due to complex perception models. The key there is aggressive pruning, smart sensor fusion, and powerful hardware. Multimodal large models, the wisdom layer, the actual model inference is ridiculously complex. It's the dominant factor. Optimization focuses on making those models smaller, sparser, or finding ways to cache and reuse computations. See how DIKWP helps us identify the real pain points in each case. It's not just about throwing more compute at the problem. It's about understanding where the complexity lives and attacking it strategically. But wait, there's more. Just counting operations isn't enough for truly intelligent systems. We need to consider the semantics. Semantic elasticity. Can your system handle different ways of saying the same thing without breaking a sweat? High elasticity means less complexity from redundant phrasing. Subject relative complexity is a task hard for a toddler AI, but easy for a human. Complexity is relative to the agent's capabilities. Semantic space flow. When information moves between layers or agents, how much meaning gets lost in translation? Poor flow means wasted effort and increased complexity. We need to weave these into our analysis, maybe extending our notation to O semantic of f of n, e, rel, phi. This isn't just academic fluff, it's about understanding the true cost of intelligence beyond raw computation. That's the DIKWP edge,